Yes, so this is the third lecture. So in the last lecture, I showed you that those differential forms, well, can be classified in three kinds, depending on where the point KL is. So the point KL, where it is in the plane. If it is inside the convex envelope, this is the first kind form, meaning that there is no pole. It has no pole. If it's on the it fits a point on the boundary, it is a third kind form, meaning that it has only simple poles. And if it is outside, it is a second kind form. And yeah, so that allows to more or less classify those forms. This is just the generic situation. In fact, it may happen, so generic in the sense that I'm just considering the situation where there is no nodal points. If there would be nodal points, p prime y would have zeros. So if there is no nodal points, all the zeros of p prime y of xy are exactly zeros of dx. So the ratio has no poles there at the branch points. But if there are nodal points, there can be zeros of the denominator that are not compensated by zeros of the numerator. So it's a less generic situation. I will not go into details. It's easy, in fact, to. So it means that you have to take linear combinations of these that have zeros exactly at those extra zeros at the nodal points. And basically, it means that the genus is not the number of interior points, but the number of interior points minus the number of nodal points, counted with multiplicity. Okay. So the genus is at most the number of blue points here, the number of interior points. So now it remains to know how to compute integrals of such differential forms. So how can we compute the integrals of such differential forms? And we shall go now to the to chapter 3, which is about the Abel map and theta functions. So the idea is to that the theta functions will make the basis of all functions that we can build on the Riemann surface, on the compact Riemann surface. So first of all, there is the notion of one will be about holomorphic forms. So which is the same thing as first kind. And I will call H1 of sigma the vector space of holomorphic forms. So it's a C vector space. Because indeed, when you take linear combinations of things that have no poles, you always get something that has no poles. So the first question will be to compute the dimension of that space. Well, you can already guess that it's the number of interior points, and it's going to be the genus. But let's see where it comes from. So first of all, consider the notion of symplectic basis of cycle. So if we have sigma, so I will always consider sigma compact Riemann surface. Of genus G. So it looks like that. And if G so if G is non-zero, there always exists a basis of cycles that looks like that. And I will give name to them. A1, B1, A2, B2. What characterizes them? So there exists basis of cycle of 2G cycles, A1, AG, B1, BG, such that AI, AJ equals 0, BI, BJ equals 0, and AI, BJ equals delta AJ. The intersection, so what we call cycles is in fact a homotopy class of cycles, or in fact a linear combination of homotopy class of cycles. And what we call intersection is not really the intersection point, it's the intersection number. So when the number is 0, it means that you can always choose a representant, some representants that don't intersect. And when I compute the intersection, it's an algebraic intersection number, meaning that if you cross, each time you cross, so if gamma 1 is like that and gamma 2 is like that, so to go from gamma 1 to gamma 2, you turn in the positive direction counterclockwise. It means that the intersection number will be counted as +1. Each time you have, on the contrary, this kind of intersection, this will count as -1. So because to go from 1 to 2, so you turn in the clockwise direction instead of the counterclockwise direction, and the intersection number is the sum of all intersections. So imagine you have two paths that do something like that. So this is path gamma 1 and this is path gamma 2. So here you have a +1 and here you have a -1. So which means the total intersection is in fact 0. And indeed, you could deform them to do something like that and like that. Okay. So the total intersection is 0. The total intersection number is invariant under homotopic deformations. So it's well defined. It goes, so it descends to the homotopy classes. It's well defined, and that's what we call a symplectic basis of cycles. So, and we usually call that H1 of sigma. And in fact, there is either H1 of sigma Z or H1 of sigma C is the vector space. So the Z or C vector space of linear combination of homotopy classes of cycles. Of closed Jordan maps. And the dimension either Z or C is 2G. So we shall admit that, so that on a G curve you can always find 2G independent cycles, and you can find a symplectic basis. So now notice I I already told you that well, we have, well, let me call the bj's, let me call them a g plus 1, a 2g, 2g minus 1. Sorry, 2g, no, sorry, 2g. Okay. So first, I have already shown you that there is, we know from last time that there exists harmonic, real harmonic forms. mu I such that integral of mu I over aj equals delta ij. And I showed you that omega I equals mu I plus I. Well, this is the square root of minus 1, this one. Star mu I, this was the Hodge star, is a holomorphic form. And it satisfies integral of ai of omega I is not really delta ij, it's just the real part of that, which is delta ij. So, well, the idea is that we want to find the. So the idea is that we have, so let me call H of sigma is the vector space, the real vector space of harmonic forms. So its dimension is 2G. We have constructed the basis, and we have a map. We have a map from H of sigma to H1 of sigma, which is the space of so that sense mu plus I star mu. So it sends harmonic forms to holomorphic forms. And this map is invertible, because if you have an omega here, you just take real part of omega. So this is an invertible map, which means that as vector spaces, they must have the same dimension. But this is a real vector space, and we would like to consider this one as a complex vector space, but it's also then a real vector space. A complex vector space is also a real vector space, so which means that the dimension as real vector space of H of sigma, which was 2G, is the dimension as a real vector space of H1 of sigma, and which is twice the dimension as a complex vector space of H1 of sigma. So which implies that dimension of H1 of sigma is G. The complex dimension, I will not write it anymore, but it's the complex dimension because I will consider this as a complex vector space. So it means there are G independent, holomorphic forms, so first kind forms. There are G independent first kind forms with independent in the sense of linear combinations with complex coefficients, which means that with real coefficients you would have 2G.
Just repeat question. Do harmonic real forms correspond to complex holonomic, or is not completely true?
Sorry?
Do real harmonic forms correspond to complex holonomic?
Holomorphic? Well, whenever you have a real harmonic form, you can construct a complex holomorphic form by doing that. And in fact, what you have here is that real harmonic forms are a real part of complex holomorphic forms. So, what I wanted to show in the end is just that you have G independent of them. So the argument is quite simple. But now the big question is, can we find a basis that would be normalized on our basis of cycles? So we will not need that anymore. But so basically that shows that the number of interior points is the genus. So question. Given a symplectic basis, is there a basis Well, this is not obvious, in fact. We had that for real harmonic forms, for a twice larger basis of cycles. But the problem is that we don't control the integrals of AI of star mu I, star mu j. Is something that we don't know. We don't know what it is. That's why it's hard to see if this theorem will be true, if this result will be true or not. In fact, it will be true, but the proof is not that straightforward, and it mostly relies on something that's called the Riemann bilinear identity. In fact, in my notes, this is 1.4, which is Riemann bilinear identities. This is a technical thing that is extremely useful and that allows to prove more or less everything you want on Riemann surfaces. This is the most, probably one of the most important theorems about Riemann surfaces. And it's based on a very simple remark. So first, in fact, it's always possible to choose the to deform our basis. It's always possible to choose representants that all start from the same single point. So let's take this as A1 and A2. So this will be A1, and we want B1 to cross this way. And this will be, well, probably with my notation it was the opposite. This was A1. And B1 with the opposite directions to pick up the other picture. And this was B2. And A2 has to go this side. Okay. Now we shall consider a fundamental domain which is sigma, where you remove, or let me call that sigma 0, is sigma where you remove all you remove all cycles. So if you want to, you cut with scissors, you take your scissors and you cut. What remains is a polygon with 2G sides. Is a polygon with 2G sides, and typically you have, let me, so this is A1, B1, that's the opposites. This is again A1 in the opposite direction, and this is again B1 in the opposite direction. Then this will be A2, B2, sorry, A2, A2, and B2. All those summits correspond to that point. And what this picture means, so this is what you obtain after cutting the surface along all the cycles. And what remains is something that has the topology of a disk. It's a polygon. And if you want to recover the surface, you should glue together. So each time you have A1, you glue it to A1, B1, you glue it to B1, A2, you glue it to B2, B2, you glue it to B2. It's like when you do that for the torus, it works for any genus. So any genus G surface can be obtained by gluing the sides of a 4J gone. Well, any Riemann surface can be obtained by gluing sides of a 4J gone. Like a torus can be obtained by gluing the sides of a rectangle.
So you mean when you glue, you respect the orientation?
Yes,
of
course,
line.
of course. That's why I put arrows. So, yeah, so what's important is that the boundary of sigma 0, is sum over I equals 1 to G of, so let me put it correctly, AI left minus AI right minus so plus sum over I 1 to G of BI left minus BI right. I hope it's correct. Another thing is that sigma 0 has the topology of a disk. And the boundary of sigma 0 has the topology of a circle. So now consider two forms. Neuromorphic form. Omega 1 and omega 2. They can have poles, and we shall assume that the poles are not on the boundary. can move the contours by homotopy, and we shall assume that the poles are not on the boundary. So there can be poles. Omega 1 and omega 2 can have poles somewhere on the Riemann surface. So which means there can be some poles on sigma 0 somewhere. Or there could be no poles. If they are holomorphic forms, it means they have no poles. But it's possible to define F1 neuromorphic, sorry. On F2 on a vicinity neighborhood, sorry, a tubular one, sorry, of on which sorry, holomorphic. So no poles on which df1 equals omega 1 or df2 equals omega 2. So which means you would like to define f1 of p equals integral from, let's say, a point O to p of omega 1. But if you look at the picture here, and we want to define that only on the vicinity, we want to define that on this shaded region. We want f to be well defined on this shaded region. This shaded region is not simply connected, because it's an annulus. So it means that if you want to compute f, you go from, so on, at a point P, let's say this is our fixed origin O. There are two paths that go from O to P. You can go this way or that way. There are two different paths that go from O to P. So it looks like this is not well defined, because you can have two different paths. But if you take the difference between that path and that path, it is equal to a sum of residues inside. And so it's 0, because the sum of residues of a meromorphic form is 0. So it means that you could define, f1 of p would be either integral from O to p on the plus side left, let's say, of omega 1, or it could be by going to the right side of omega 1. But the difference between the two, integral of OP left minus integral of OP right, is a closed integral so maybe the picture here, you go either this way or that way. So when you take the difference, you get the full circle integral. Agree?
Could you also compute this by saying that this is an integral of d sigma 0, and then d sigma 0 has, for example, a left minus a right, so if you integrate over a left minus a right, you get 0.
That's what I'm going to do next. That's going to be Riemann by linear identity. But for the moment, this is just the definition of F1. No, it's not. No, because F1 is does not take the same value near here or near there.
No, but I'm starting from integral of omega 1 now.
Yeah.
Integral of omega 1 over some contour which is actually d sigma 0.
No, it's a contour that has an origin and an end. It's a chain. It's not a closed contour. It's an open contour. But the difference of the two is indeed a closed contour integral.
But you put the 0. At which point do you put the 0?
An arbitrary point. I mean, well, I just want to say that there exists some f1 with differential is omega 1. But I want just f1 to be well defined in all the shaded region here and to be holomorphic in that region. But f1 is discontinuous. I mean, f1 is well defined on that region of sigma 0, but it's not well defined on sigma. So meaning that it can take different values on the different sides of an area contour. So the Riemann bilinear identity is the following theorem. So this is the main theorem. Riemann bilinear identity. And it says that integral of f1 omega 2 integral over d sigma 0 of f1 omega 2, which is also, by integrating by parts, the same thing as minus integral over d sigma 0 of f2 omega 1 is equal to sum from I equals 1 to g of integral of a, let me take it correctly, ai omega 1 times integral of bi omega 2 minus integral over bi omega 1 integral of ai omega 2. You can notice that it is antisymmetric, and it defines a symplectic form on the space of holomorphic on the space of homomorphic forms. Well, it's a bilinear antisymmetric combination. And this is the main theorem, and it is extremely useful. So the proof, in fact, we have more or less all the ingredients of the proof already, and it's more or less what Sylvain just said. So as I said, what is the difference of, let's say, f1? For f1, if you take something that is on the left side, so this is the left side, and this is the right side of bi, okay, what is the difference between the two values? So f1 is discontinuous, and it's discontinuous across across ai or bi, and across ai, you have that f1 left minus f1 right equals, well, of course, the difference between the value here and value there is, or if you want on that picture, the difference between here and there is the integral from here to there. Okay? Or you can see it on that picture, it's the integral from here to there. And it's the same thing as the A-cycle integral, as the B-cycle integral, sorry, for AI. So this is minus, and same thing for F2, F1 on BI, F1 left minus F1 right is plus this time AI omega 1. And if you combine this with that, basically you get the result. So because the left-hand side here, you decompose it as such integrals. Omega 2 is continuous across all the cycles. Omega 2 was meromorphic, it's continuous. But F1, omega 2 is continuous, but F1 has a discontinuity. So omega 2 takes the same value on AI left and AI right, but F1 does not take the same value. It takes a value that's the difference, and the difference is a constant. It does not depend when you are on the cycle, and it's itself a cycle integral. So basically you get the Riemann by Eynard identity theorem. So there is a corollary. So take omega 1 and omega 2 holomorphic, so without poles. So without poles, then F1 and F2 can be globally defined on sigma 0. And which means that this integral here on the boundary can be contracted to 0. So the left-hand side was 0. So which means that 0 equals sum over I equals 1 to j of integral of AI omega 1 integral of BI omega 2 minus integral of BI omega 1 integral of AI omega 2. Okay. But that's not the most useful we shall use now. In fact, I shall use that again later. But in fact, there is another thing which is the Riemann by linear inequality now. So now I take the Riemann by linear inequality. I will so take omega and omega equals df on sigma 0. So take omega a form without poles. Then the double integral, so then what we have is that if we take this, and here we shall take the complex conjugate. So we take a complex conjugate like that. It's the same thing as taking, and here we shall take omega and again the complex conjugate. Okay. You multiply this by 2i. So this is the square root of -1. This is positive. I times this sum is positive. So if omega is non-identically 0. the proof is more or less the same thing. It's the Stokes theorem. It's when you take the double integral on sigma omega wedge omega bar. In fact, you multiply by 2i. So locally, remember that omega locally is something like a certain function, let me call it g, of z times dz. So omega bar will be g bar of z times dz bar. And remember that dz bar is not the two-dimensional Lebesgue measure. It's 2i times that is the two-dimensional Lebesgue measure. So this is real positive. So that's why we have to multiply by real by 2i. So this is positive because it just means this is the same thing as integral of modulus of g to the square times d to z. So this is strictly positive if omega is non-vanishing. Now we use Stokes theorem for that. So on sigma, so this is an integral on sigma, but we can say it's an integral on sigma 0.
Sorry, I'm confused about what is the dependence of omega bar? Does it depend on z or?
Yes, in fact, it's the same thing as g bar. Sorry. So it just
bar.
Sorry.
It
should be that. Sorry.
Okay.
So sorry, the constant doesn't really matter, but I think it's over 2i.
Over 2i.
I mean, it doesn't matter the 2, and the I can be
You're
negative.
right. You're right. So it's over 2i.
Well, no, actually it is important because otherwise the sign changes.
Sorry.
Yeah, it was important actually because the sign would change.
Okay, I will. Maybe I made a mistake in my notes then, but okay. Okay. I will check that carefully later. Okay. dz bar is minus 2i. Is this one correct?
Yes. Yeah. That's correct.
So then it's minus 1 over 2i. That is positive. Okay? So it's just an I over 2 instead of 2i.
For to carry this computation, you represent z as the sum of real and imaginary
Yeah,
parts,
yes.
and then you
Okay. It doesn't matter too much. What I just want to say is that if we apply the Stokes theorem, so the Stokes theorem says that integral of sigma 0 of omega wedge omega bar is the same thing as integral over d sigma 0 of f bar omega. And if you compute this as before, so this is so omega is continuous across the boundary, is continuous along the boundary, but f bar has discontinuities, and you use the same formula as before. It's probably written here. So you use that boundary is this sum, and f has discontinuities. And basically, you find the right-hand side, so you find sum over I of integral of ai of omega integral of bi of omega bar minus integral over bi of omega integral over ai of omega bar. And that gives the theorem. So let's study one important corollary of this theorem. So now we go to normalized basis. And this will be theorem 2.1. An important theorem is that there exists, so given a symplectic basis of cycles A1, AJ, B1, DJ, there exists a unique basis of H1 of sigma such that integral over AI of omega j equals delta ij. How do we prove that? Well, proof. If we consider the map from H1 of sigma into C to the j, g, that to a form associates the vector, let me call that map epsilon. So epsilon, it maps to the vector epsilon equals epsilon 1, epsilon g, where epsilon I is the integral over ai of omega. So this map, so the two, and we already know that the two spaces have the same dimension. All what we need to prove is that, so we want this map to be invertible to have the theorem. So to get the theorem, we want this map to be invertible. So we just need to prove that it's injective. So we need to prove that its kernel is vanishing. So let's. Omega belongs to the kernel of this map. This would imply that for all I, integral over ai of omega will be 0. Okay. Now let eta I be the bicycle integral. We don't know what it is. Okay. But with the Riemann bilinear identity, we know that sum of eta I ai bar minus epsilon I ai is positive or something like that. Minus epsilon, sorry, what is it? Sorry, we know that the imaginary part, imaginary part of sum over I equals 1 to g of epsilon I eta I bar is positive. Which is impossible if all epsilon I vanish. So maybe
is it positive or negative?
It's negative.
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 Doesn't matter, I just want non-zero.
Yes.
Okay. So which means that the kernel is vanishing. So the map is injective. So then we know that this is injective. So it is a bijection. It is an isomorphism. So which means that it's possible to find the inverse of vector 0, 0, 1 it's possible to find the inverse of delta ij. So there does exist a symplectic basis, and you see it's quite subtle. The reason why it exists is because of this positivity of a two-dimensional real integral, and it's based on this Stokes theorem and all that, so it was not so straightforward.
So the proof doesn't go by construction?
Sorry?
The proof is not constructible? Or, I don't know, okay, otherwise you can just have arbitrary linear
I don't know.
forms and then have the inverse.
I don't know, but it's just that it's not that straightforward. And for instance, there are possibilities to work with curves not on C but on a field, for instance, a finite field. And then you don't have Stokes theorem. Okay, it's more subtle. So so now a definition. The Riemann matrix of periods. Tau ij. So we have chosen our basis. So we have our basis integral over ai of omega j equals delta ij. And we define tau ij is the integral over vi of omega j. And there will be a theorem. Tau ij equals tau ji. And the imaginary part of the matrix tau is positive definite. So as a matrix, the imaginary part of tau is a positive definite matrix. So the matrix is symmetric and positive definite, and those two properties together means that tau is a Siegel matrix. Well, the Siegel space is the space of all positive, so is the space of all complex matrices that are symmetric and whose imaginary part is positive definite. And it's of dimension, you can see that locally it's a manifold of dimension, which is g plus 1 over 2. Well, just the dimension of the space of positive complex dimension, I mean. So for real dimension, it's twice that. So every Riemann matrix of period is a Siegel matrix. The converse is not true. There are many Siegel matrices that are not. So this is a remark. For G larger than 2, there exists Siegel matrices that are not a characterization of the space of Riemann matrices of a subset of the Siegel space that is made of Riemann matrices is given by the Krischever-Novikov. Well, it was called the Krischever-Novikov conjecture. They conjectured characterization of the space of Riemann matrices within the Siegel space, but this conjecture was later proved. I'm not totally sure, but I know that Moulassé, well, it did not fully prove it, but he proved basically what allows to prove it. Well, I think there was probably a line missing to say that it was proved, as far as I know. Well, I would not be unfair to someone Okay, but so just to say that not all single matrices are Riemann matrices of periods. So yes, sorry, I forgot to prove the proof of the theorem. It's again just Riemann bilinear identities. So this one is just Riemann bilinear identity by taking omega I on omega j, and this one is again Riemann bilinear inequality. So it's just the same as before. So as I said, the Riemann bilinear identities allow to prove lots of things. So now let me define something which is the Abel map. Of theta functions. So to a point of sigma, I want to associate something. So to a point P, I would like to associate the vector that I will call U1 of P, UG of P, where UI of P is an interval from a given point O to P of omega I. Okay. This is not really well defined. This is not really well defined because so first we shall choose O, a generic point of sigma. We shall choose it once for all. So we choose a base point somewhere. Okay. So we would like to define this map. It is not well defined. So basically, dy equals omega I. It is not well defined because when you want to go from O to your point P, it depends whether you go there or you could go. I don't know. There. Okay. And it will give different results. So in fact, it's only well defined on the universal cover of sigma. Or if you want, instead of a universal cover, you could also choose to define it on sigma 0 on the fundamental domain. So it's not that well. So it's not well defined. But what we have is we know that if we go from a different path, so if we take different So what is really well defined is that if we go from sigma to sigma g, but we quotient out by, so basically we shall identify ui equals ui plus an integer number plus z, or plus tau I j z for all j. So basically, meaning that if you go from P, from O to P by a different path, it means you can have added an A cycle or a B cycle or an integer linear combination of A or B cycles. So which means that modulo integers or modulo integer times the integral over B cycles, you will get the same result. So let's quotient. That's what we write like that. Now to P, that P associates the vector ui, u1, ug, modulo z P plus tau ZG. If you have G equals 1, this is just the usual thing on the torus. If you are in genus 1, you have a map from your surface sigma, so which is a torus, to the parallelogram 0, 1, tau. And you're just saying that to a point P, you associate the point U of P, which is a point in the complex plane, and you identify it to U of P plus 1, so it's the same point, or you identify it to U of P plus tau. Well, in genus 1, tau is a 1 by 1 matrix, it's just a complex number. And so this is C constituted by Z plus tau Z. And it's the standard torus. So it just generalizes to that. I just want to say that this quantity, this space is called the Jacobian. Of sigma. So the Abel map is a map from sigma to its Jacobian.
Sorry, so if you take a fundamental domain in CG, do you get your 4G code which you had before?
Yes, in some way, except that so now this space is of dimension of complex dimension G, CG. Indeed, you get you get a submanifold. So, and indeed, well, I mean, this is a space of dimension 1 that is mapped into a space of dimension G. So you get a manifold of smaller dimension, and indeed, it is a kind of 4G gone. Yes, it's difficult to visualize. For G equals 1, the two sides have the same dimension, and it's really a bijection. We shall see it later, but it's injected. Not 2 points that can be sent to the same point. So this is so we have a map from so maybe we should take a break now. I will then do the theta functions. So theta functions are really defined on C to the G, and by composing the two, we will be able to build really elementary functions from sigma to C. So I go on with the definition of, well, there are many different theta functions that exist, but there is one that is called the Riemann theta function. And if you are used to elliptic Jacobi theta functions, I think this is the theta 3 of Jacobi. This is the one that has its 0 at the center of the parallelogram. So it's theta 3. Okay. The Riemann theta function is defined as follows. It's a map from CG to C. That's to a vector U equals U1 UG associates sum over all G uppers of integer numbers of exponential 2 pi I. Let me write it, well, sum of ui and I. equals 1 to g, so it's the scalar product on exponential pi I, sum from I j equals add 1 to g of ni tau ij and j. Well, very often we shall write it this way, n belongs to zg of exponential 2 pi I un exponential pi I n tau n, scalar product. I should write. So it's not periodic. It's not periodic, but it's quasi-periodic. So properties. So theta, sorry, we shall call it theta of u on tau. Very often I will not write the tau. Okay? I will assume that tau is fixed once for all, and I will just write theta of u. So theta of u plus n, if theta of u, if n belongs to zg. So it's periodic in that direction. Of course, it was a Fourier transform. But theta of u plus tau n is theta of u times exponential minus 2 pi I of un plus 1/2 of n tau n for an integer vector. So for n belongs to zg. So there is a phase. You pick a phase when you go so along integers it's periodic, and on tau in the tau direction it's not periodic, it's only quasi-periodic. Well, it has another obvious property, which is that theta of minus u equals theta of u. So it's an even function. It's an even function, and you just, all those properties are quite easy to prove from the definition. Well, if you combine those three properties together, you can easily see that if A and B are, so if A belongs to zg and B belongs to zg, and if the scalar product fb is odd, so this is just sum of ai bi. So if this number is odd, then theta of 1/2 of a plus tau b must be 0. You just combine. Basically, by combining those relations, you find that theta of this quantity equals minus theta of the same quantity, so it has to be 0. So we know some zeros of the theta function. Oh, I just forgot to say that it's well defined, it's absolutely convergent for any u. So this is absolutely convergent for every u belongs to Cg, and it's uniformly on any compact domain. Well, basically, it defines an analytic function of u. It's so theta of u. So should write it in the properties. That's theta of u is analytic function of u, which is u1, ug. It's an analytic function of all the components. And there is no pole on CP. It's always well defined, and it's always analytic. So now we have the Abel map that goes from the curve to CG, and we have the theta function that goes from CG to C. So it's tempting to combine the two. So I probably already mentioned those references in the first lecture, but you can look for the exact references, but these are good introductory book on the subject. Okay. So now the idea is that those theta functions will play exactly the same role as, will be kind of building blocks to build meromorphic functions. Let me go back to genus 0. Genus 0 and the Riemann sphere. So which is C, well, which I write this way. C union the point at infinity. Every meromorphic function f can be written in the form f of z equals a certain constant times product of z minus, let's call them qi, I equals 1 to r, over product of I equals 1 to s of z minus pi. Well, if you want, it's a product of monomials divided by a product of monomials. So any rational function is a product of things that have only a simple zero divided by a product of things that have a simple zero.
Question about the definition of Riemann. So you have these integrals over n forms, and you choose them as the basis of these cycles.
Yeah. 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 So it's just that, so basically the idea is that a rational function, so a meromorphic function, is a quotient or is a product of monomials.
Why do you forbid multiple zeros on poles?
Sorry?
Why do you forbid multiple zeros?
I don't forbid them.
Okay,
I don't
okay,
say
okay.
that they are distinct. So basically the idea is that any meromorphic function is a constant times a product of elementary building blocks divided by a product of elementary building blocks. And basically we shall have now the same theorem for all genus, but replacing the monomials, so the thing that has only one simple zero, by theta functions. So that's the idea. So how do we do that? So how do we do that? So first, let me define the map from sigma 0 to C, that to a point P. Let me define the map G zeta Q, where zeta belongs to CG and Q belongs to my Riemann surface. That's to P associates G zeta Q of P is theta of U of P minus U of Q plus zeta. Okay, why not? Well, how many zeros? Well, first, this has, as I said, this has no pole. G zeta q has no pole. Since it's just the theta function, it is discontinuous along a cycles. So, in fact, it's continuous along a cycles. So, which means that G zeta q of P on AI, so if P belongs to AI left equal G zeta q of P on the right, whereas on for B cycles we have G zeta q of P left equal G zeta q of P of Q of P right times exponential minus 2 pi I ui of P plus 1/2 of tau II. It's the opposites. It's on the B cycles.
Where's the I dependence? It seems your phase
Here?
factor yes has the I dependence. Where is it? Oh, it's AI.
It's
Okay.
AI.
Yeah.
Yes. So yes, like AI. It's here and here. So these G are going to be the monomials in some way. So first of all, so proposition is that G zeta q has so the number of poles has G poles in sigma 0. Let's call them P1, Pg. And we shall have a property.
Zero.
Sorry, zeros. Of course, sorry. It's sigma 0, and the property is that. Sorry, what is the property? No. Well, sorry, let me write that as a lemma. If we choose zeta equals if zeta equals 0 of theta, so if theta of zeta equals 0, we have two possibilities. Either that or G zeta q is identically 0 for all P. So either it's the vanishing function or it has exactly G zeros, and one of them, sorry, Pg minus 1, and one of them is obviously Q. And I will complete the theorem saying that U of P1 is called the Riemann constant. So it belongs to C to G, and Ki equals, so the ith component is the I component is minus 1 of tau I plus minus sum over j equals 1 to g of integral over aj, aj of uj dui. Just a certain constant. So that's my lemma. So if
K is G of
sorry, in that case we say that zeta is a singular zero. So if zeta is a zero, such that the function g zeta q is identically vanishing, we say that zeta was a singular zero. But in fact, there are very few singular zeros. Most zeros are not singular. So how do you prove that theorem? In fact, it's again Riemann bilinear identity. So the proof is Riemann bilinear identity. So which means that you shall write that, for instance, integral over sum. We shall say that sum of residue of d zeta q over d g zeta q. So you shall take the logarithmic derivative sum of zeros of g zeta q. So let's call them pi. Okay. So if we have again our big polygon, we have g zeta q has a certain number of zeros. Its logarithmic derivative has poles there. The sum of residues of all poles is the number of such zeros, and you can deform the contour to say that it's equal to that integral. So it's 1 over 2 pi I integral over the boundary of sigma 0 of d log g zeta q. And again, you decompose the boundary of sigma 0 into sum over left side minus right side of all A on B cycles. And you have that nice property that you know what is the difference of log of G across the the B cycles and the A cycles. So you just, so what you end up with is that the sum of basically, and you see when you take the log, you just have to take the phases. So you do that carefully, and you find that, you find that this is just the genus. So the total number of points is the genus. The total number of points is the genus, and if you look at this function and assume that theta of zeta equals 0, so if zeta is a 0 of theta, then you see that this obviously vanishes when p equals q. So one of the zeros is q. And give a name to the other points, p1, pg minus 1. Okay. So to summarize, you have your Riemann surface. You have that, on it, you have your function G zeta Q, and it has a certain number of zeros. One of them is Q, and there are a few others. So if we are in genus 2, or if we are in genus 3, there are P2.
Sorry, you include the Q in the sum of the residues.
Yes.
But you do not include the Q in the statement which defines
okay,
K.
let's call them P tilde I, and you don't know yet what they are, but it's just all the zeros.
Okay.
All zeros.
And above you exclude, when you define K, you have no...
Yes, yes. In fact, the definition of K is this one, and this identity is the lemma, is what you prove.
Yes.
This identity is a fact that you prove. To prove the second part of the lemma, you use again Riemann by linear identity, but not on the function dg zeta q over dg zeta q, but you use the same, again, the Riemann by linear identity with that times. So you use it with what function? Well, you multiply by uk. Well, you just multiply by uk. And so this will give, this will just give, by definition, this will just give some over, so which will be uq plus u of p1 uk, p1 plus uk of pg minus 1. Okay, and again, working with a bilinear identity, you find that this is uk of q plus k xk. Okay. Again, using Riemann bilinear identity. Basically, using just those properties.
What happens for
I
G for
forgot,
zero?
sorry. It's because I forgot something really important here. This was wrong. It was, of course, minus ui of q plus zeta I plus 1/2 of tau oi in the face, sorry.
What happens for G equals 0?
Okay, so this theorem was only for G strictly positive. In fact, for G equals 0, there is no holomorphic form at all. All this is, for the moment, only for G positive. In fact, for G equals 0, we have this decomposition of rational functions as product on ratios of. I will come back. It's in the notes. In fact, in the notes, I start by proving that for G equals 0, there is no holomorphic forms, and we know how to. There is every genus 0 surface can be holomorphically mapped to a Riemann sphere. So it's in the notes. I will not do it now, but it's in the notes. So okay. So the subtle property. So the subtle property is that, in fact, so a priori. So a priori, since P1, Pg minus 1 seem to be, well, they seem to be functions. So they are the zeros of G zeta Q. So you could think that, so P1, Pg minus 1, that are the zeros of G zeta Q. So you could think that they are functions, they depend on zeta and Q. The important property is that, in fact, they don't depend on Q. As you see already, you see that their able maps do not depend on Q. You see that the sum of their able maps does not depend on Q. That's a good sign. But now you have to prove that they do not depend on Q. Well, I do it in the notes in details, but this is more or less based on the fact that, well, the set of zeros of theta, we shall call it, so theta equals, so it's the set, so what we call theta like that is the set of zeta belongs to CG such that theta of zeta equals 0. So it's locally a codimension 1 manifold of CG, so it's locally a dimension G minus 1 manifold.
So does it follow from the analyticity of this function?
Sorry?
Does it follow from analyticity of this function that there is at least one zero and there is the dimension of the number of zeros is large? How do you prove that this theta function has, I mean, at least one zero at all?
Well, we showed that the half integer, you remember, 1 of A plus tau B. We already proved that this is 0 for A if A scalar B is odd. So we know that there are at least a few zeros, but otherwise it's, yes, indeed it's an analytic function, and so it has to take the value 0, and typically it's a dimension G minus 1 manifold. On the torus, this is a dimension 0 manifold, it's a set of points, and in fact it's only 1 point. But, okay. So these zeros are indeed special zeros. So basically this is a dimension G minus 1 0, and we have a map. We have a map from theta to sigma to G minus 1. Sorry, I should write it the other way around. If we take, no, sorry, this is the right way. So we know that for every zeta belongs to theta non-singular, there exists P1 G minus 1 that belongs to sigma to G minus 1, such that zeta equals, so it was written, it's because I made a mistake, it was K minus zeta, where this was the Riemann constant, sorry, the theorem was that one. So such that zeta equals K minus U of P1 minus U of G minus 1. The converse is true as well. If you take the map from sigma to J minus 1 to theta, that's to P1 PG minus 1 associates zeta equals K minus U of P1 minus U of P2 minus 1. Sorry, This is not exactly true. What is the space? So the idea is to say that there is a kind of bijection between zeros of theta and a set of g-1 points, because both are dimension g-1 manifolds, and this bijection is in fact independent of Q. And so you see that to every zeta you can associate a set of points. A priori they will depend on Q, but the inverse map, so knowing your g-1 points, you can recover zeta by this formula. This does not depend on Q. So the inverse map is independent of Q. So this shows that in fact the map is independent of Q. I will not enter into the details, it's well written in my notes. But the main theorem that I want to say is the following. By the way, the theta function is implemented on any Mathematica or Maple or whatever software, and it converges quite well. So you can actually do computations with it. So the main theorem that I want to say is that so theorem. I'm sorry, theorem for every f neomorphic on sigma so we let with zeros pi of multiplicity of order, alpha I on poles pi of order also alpha I. Or zero or poles. So it just means that the zeros have positive order and the poles have negative orders. Okay. The poles have negative orders. Then and let zeta equals non-singular 0 of theta. There exists C, so F non-vanishing, such that F of P equals C times product from over this I of G zeta Pi of P to the power alpha I. So this is exactly the same kind of thing we had for. Remember that g zeta of p is a function that vanishes at p equals pi. G zeta of q, g zeta. Remember that g zeta q of p equals 0 at p equals q, because it was in fact theta of. So let me write this as follows. So it's C times product of theta of u of p minus u of pi plus zeta to the power alpha I. So you see, since theta of zeta equals 0, this obviously vanishes at p equals pi. to the order alpha I. So this is, so you see that the right hand side has the good poles on zeros. But question, is it a meromorphic function on sigma? It's not that obvious. Because the answer is that yes. And we, and it implies that, sum of alpha I of u of pi so every meromorphic function has to satisfy that. How do we prove this? Proof. Well, first remark is that under what condition is the right-hand side indeed a well-defined meromorphic function? So take the product of theta of u of p minus u of pi plus zeta to the alpha I, and compute the discontinuity. So is it continuous across A and B cycles? And across A cycles, it has, so across B cycles it's obviously continuous because across B cycles you add to u of p an integer, and theta is periodic. So it's continuous across B cycles. J. But across AJ, it's not continuous. A priori not continuous. Across AJ, and then, so let's call that function f tilde of p. So we have that f tilde of p left over f tilde of p right. Remember, this is the sum of exponential minus 2I pi sum over I alpha I times so it was uj of p minus uj of pi minus theta j minus 1/2 of tau jj. So remember that for a meromorphic function, we know that the number of poles equals the number of zeros, so sum of alpha I equals 0. There is as many poles as zeros. Remember, zeros have positive orders, poles have negative orders, and the sum of all orders must be 0. So which means that here in that sum, in the sum over I, this plays no role. And uj of pi also. So which means that in the end, this exponential phase is just exponential minus 2I pi sine sum of alpha I uj of pi. Sorry, when I say equals 0, mod zg plus tau zg. So I'm in the Jacobian. So you see that this is So you see the condition under this f tilde would be a well-defined neuromorphic function on the curve would be that precisely this is satisfied. If it is not satisfied, then this is not a neuromorphic function. Now, but anyways, let's say that for the moment it has discontinuities. And let's compute the function f of p over f tilde of p. Well, it has no poles and no zeros. By definition. But it could have discontinuities. Now take the d of log of f of p over f tilde of p. So the logarithmic. So this is a one form. Well, since the phase here is independent of p, okay. Since the phase here does not depend on p, it means that the differential of log of that is 0. The differential with respect to p of that quantity is 0 because it's independent of p, it's a constant. So which means that omega has no discontinuity. And no pole, which implies that omega is a holomorphic one form. Let me continue the proof here, which implies that there exists lambda 1, lambda j, such that omega is sum of lambda I, omega I. Which implies that now you integrate, you take the exponential, which implies that f of p over f tilde of p must be the exponential, so exponential of sum of lambda I ui of p times a certain constant. Let me call that index k. But now we know it's still written here. When we go across a bj cycle, we know that this has no discontinuity. And we know that the uk's are shifted by integers. So which implies, the fact that it's continuous across b cycles means that all lambda k's must be integers. And sorry, what was I saying? But then it will not be compatible. So basically, what I want to say is that the lambda k have to be zeros. When you go now across an A cycle, this has to be equal to that. So this means that sum of lambda k uk must be tau kj must be equal to sum of alpha I u j of pi. So which means that, which exactly says that this sum of alpha I uj of pi is an integer combination of the taus, so it belongs to tau zg. So which implies that sum of alpha I ui of p belongs to zg plus tau zg. Which implies that f tilde was indeed has no discontinuity. And now f over f tilde is a meromorphic function without poles, so it must be a constant. You all agree? It's a long way, but in the end, so which implies that f tilde is meromorphic on sigma, and thus f over f tilde must be a constant, because it's a holomorphic function without poles. It's a meromorphic function without poles, so it must be a constant. You agree? So we have obtained the generalization of the theorem saying that any rational fraction is a product of monomials to some powers, positive or negative. It's to say that any meromorphic function on the Riemann surface is a product of theta functions to some powers. Sorry, oh, I forgot some important thing. Yes, sorry. When I say that this has no poles, when I say that it has no poles nor zero, okay, I mean each g zeta, so each theta function vanishes at p equals pi, but it vanishes at g minus 1 over points. But somehow this, but since, as I said in the previous lemma, those g minus 1 over points are independent of the pi's, they are the same for numerator and denominator, and they all cancel out in the end. So that's why you have this. So it relies on the previous results, which I forgot to say. Yeah.
I guess that there is a missing 2 pi I factor in the lambda. When you say
yes,
omega, because otherwise you do not have the, I mean, you need the f over f tilde equal to some exponential 2 pi I.
Yes, you're right, you're right. It's 2 pi, yes, sorry, it's 2 pi I. Yeah, so if you are, okay, I was probably a little bit too fast, but if you do things carefully, yes, because also here it's 2 pi I that.
Yeah, the better is to rescale lambda.
Yes, yes. So write a 2 pi I here, and then you have really lambda belongs to z, and also this is this must also be, well, there is also a 2 pi I here. So in the end, everything should be okay. It's just I was a little bit too fast. So I just want to introduce the notion. I will stop here. I just want to say one word about the notion of divisor. Def, a divisor. D is a linear combination of points. Pi belongs to sigma, and alpha I belongs to Z or C, depending. So it's just a formal linear combination of points. It's just a formal linear combination of points. Okay. Whatever. It's just a formal linear combination of points. We shall define Abel map on divisors.
So the PIs have no property.
No property at all. We shall define the Abel map on divisors as U of D is just by definition sum of alpha I U of pi. So just by linearity. We shall also say that the divisor, so divisor of a function f, we shall note it f, is sum of alpha I pi, where pi are the poles and or zeros with order alpha I. And we shall, with a form, one form, omega, we shall write omega equals sum of alpha I pi, one with the same definition. And what we have proved here, so we basically the theorem is that for every f neuromorphic function, we define the degree of D is just sum of alpha I. We have degree of f equals 0 and U of f equals 0 in the Jacobian. In fact, the reciprocal is true as well. For every divisor D, degree of D equals 0 and U of D equals 0. Sorry, let me take the only in Z. And U of D equals 0, then there exists f such that f equals D. So the divisor of degree 0 and of Abel map 0 are precisely the divisors of neuromorphic functions. And there is something which I will not use at all, which is the Picard group, which is the set of divisors quotiented by the set of divisors of neuromorphic functions. And the Abel map is well defined. Due to this property, the Abel map is well defined on the Picard group.
Can you give definition in your notes?
Well, it's the set of divisors.
You see coefficients.
Sorry?
When you say set of divisors, you see coefficients.
Yes. On C. Quotiented by the divisors of functions. Well, I will not use it, but it's just nice to know that it exists. And the fact that it's an interesting object is really due to this property that the Abel map vanishes on divisors of neuromorphic functions on the degree vanishes. So I stop here. Next time, I want to talk about the Riemann-Rohr theorem. Riemann-Rohr theorem is basically the question of, given a divisor, given some points on some degrees, is there a function that has that vanishes or has poles at both points with the given degrees or less? So I mean, it has a pole of maximum that order, of that maximum minus alpha I. It has no pole. Or if you give a 0, you say that it vanishes at least at this order. So there will be a notion of ordering of divisors. And the question is, can you find a function that vanishes at some points at least with an order, or as poles of at most a given order at some points. And how many such functions are there? Of course, this forms a vector space. So what is the dimension of a vector space of functions that have at least given zeros or poles?
What happens if the degree of the divisor is equal to 0? Does it have immediate answer? What is the space of these functions? Or not?
Sorry?
So
If you just take degree of divisor equals 0, but Abel map non-zero. So here you want two things. You want to have degree equals 0 and you have d equals 0.
So the dimension depends on some other quantities. The dimension of the quantity of the number of such functions that you mentioned in Riemann work.
Yes, so it's the object of the Riemann work theorem, and it's a beautiful theorem of algebraic geometry, and I will do it next time. I cannot answer in 1 minute.